Hello students, in this video we'll discuss the null space, the range, and orthogonal complements. Let's let A be an n by n matrix. Then we have the following relations. We have that the null space of A transpose is equal to the range or the image of A perpendicular orthogonal complement. We have that the range of A transpose is the null space of A perpendicular. We have that the null space of A is the range of A transpose perpendicular. And we have the range of A, the range of the matrix, or the image of the matrix, is equal to what? Is equal to the null space of A transpose orthogonal complement. Now remember, these are sets, so do subset inclusions, right? So what we're going to do is we're going to prove all of these relationships, but we're going to sort of use properties of the orthogonal complement as well as properties of the transpose. So there are two properties of orthogonal complements that we're going to use. So recall, we have two fundamental properties. We have that A transpose, if you do the transpose twice, you get back to A. And also, if you have a subspace U, if I have a subspace U, I do the orthogonal complement of the orthogonal complement, we know the orthogonal complement for a finite dimensional space, as we are in this situation. For finite dimensional space, this is equal to U, right? And this is only true for finite dimensional spaces, Okay? There are instances in infinite dimensional space where U is strictly contained in the orthogonal complement of the orthogonal complement. But these two relationships will allow me to sort of symmetrize these expressions over here. So now, let's focus on the first expression over here. So let's call this over here statement 1, call that statement 2, statement 3, and statement 4, right? So let's focus on statement 1 over here. So how do we do statement 1? So statement 1. Okay? So let's let X be in the null space of A transpose, okay? So what is the necessary and sufficient condition for X to be in the null space of A transpose? That this is true if and only if what? If and only if A transpose X is the zero vector, right? So that's just the definition of what the null space is, right? The zero vector. But if A transpose X is equal to the zero vector, this is true if and only if for any Y in your n-dimensional space, Rn, we have A transpose X dot Y is equal to 0. If A transpose X is the zero vector itself, it's irrelevant what I dot it with. It will always give me 0, the zero scalar in this case, right? Now, of course, by properties of transposes, I know I can put the transpose on the other side of the inner product. This is true if and only if X dot A transpose Y is equal to 0, right? And then what can we say about this? Well, A transpose is exactly just what? That's exactly the same thing as just A by our lemma over here, right? So it's going to be X dot A Y is equal to 0. So in other words, for X is in the null space of A transpose, if and only if for every Y in Rn, this is in what? That's in the range of Y. So AY is in the range of Y. So AY is an element of the range of A. Okay? So in other words, X is what? X is orthogonal to everything in the range of A, which says that if and only if, this is true if and only if X is in the range of A, orthogonal complement, range of A, orthogonal complement, and that proves statement 1, okay? So statement 1 is actually all these statements are equivalent to each other, so I'll show you how that goes. So what we can do is the following. So if I wanted to get, for example, if I wanted to get from 1 to 3, for example, right? What could I do? I could apply 1 with A transpose. So apply 1 with A transpose transpose, in other words, I'm going to replace A with A transpose, right? To get what? To get the null space of A, which is the null space of A transpose transpose. Now I know the null space of A transpose is just the what? By statement 1, that's just the range of A transpose perpendicular, right? So that proves, so in other words, statement 1 proves statement 3 by the double transpose rule, right? Excellent. Now, how can I get from 1 to 4, for example? I can go from 1 to 4, going from 1 to 4, 1 to 4. What will I do over here? What I'm going to do is I'm going to take the orthogonal complement. So take the orthogonal complement of 1. If I do so, we'll get the null space of A transpose perpendicular over here, that's the left-hand side, is the range of A perpendicular perpendicular. Range of A perpendicular perpendicular. But we know from this finite dimensional statement that the double perpendicular, the double orthogonal complement, is just the original space, just the range of A, right? Excellent. So now I have 1, I have 3, and I have 4. I just need to get to 2. So now what I can do to get to 2 is I can apply this result, 4, apply this result, so take this and apply to A transpose, which is equal to A. So in other words, if I replace A with A transpose transpose, I will get result number what? I'll get result, I can apply this to A transpose, the double transpose will get me back to this thing over here, so I'll get number 2 if I apply this result to the transpose. So by proving one of these results and using the fact that the transpose of the transpose is equal to the matrix itself and the double orthogonal complement is the original subspace, I'm able to prove all of these equivalent statements, and these are very, very useful in terms of solving linear equations and figuring out when the dimension of a certain subset of solutions is larger than other ones, and we'll see how we apply these results in further videos. Thank you very much.